Hi, Srini. Hope you get your things done. Okay.
Hello, Chair.
Ready to start?
Oh, 1 minute, Chair. Yeah, hello, Chair. Ready to start.
Okay. We have completed 21.1, 21.2. I hope you have done the homework. We'll spend some time going over the answer. Then 21.3, intensity level of sound.
Oh, Chair, did you know the school, right, Chair?
Say again.
The school?
The school, yeah, about the school.
Yeah, 2 hours ago only came out the news, teacher. They're going to delay another 1 more week.
Give you all 1 more week holiday.
No, because of the flood, lah, Chair.
Your place affected, right? Your school?
No, the whole Malaysia 1 week affected.
Oh, okay. Got some
So school open at 10 January, supposed to be 3, but then now open at 10.
Okay. I think some school may be affected also lah. Some student or family may be affected. That's why they close the school.
Yeah, Shalam, they're very bad, Chair.
Yeah. Mismanagement. Okay, let's carry on. Intensity level of sound. Right, page 92. Right, we are supposed to define and calculate the intensity level of sound. Okay. Right, intensity we have defined earlier. Right, there's a source there giving out energy, a point source giving out energy. The rate of energy that's given out is P. And then that energy is spread out. Right, at distance away is spread out over the circle or over the sphere. Right, so we define intensity as a rate of energy per unit time.
Chair, I can't see that screen or yours, Chair.
Can't see the screen. Oh, sorry.
I mean, I can only see the clock.
Okay, sorry. Right, intensity we have defined earlier. Now just reviewing it. Intensity is the rate of energy. Rate of energy is the power falling normally per unit area on a surface. Right? So the surface must be perpendicular to the ray of light or the beam of light. The power is in watt. Area is in meter square. So that's a unit. Watt meter minus 2 is a vector, just like electric field strength. Intensity of wave is proportional to amplitude square. Okay, you can rewrite it as that, or you can write it as I equals to Ka square. K is a constant. Right? It's a point source. Right? Point source give out energy P. Rate of energy given out is P. Then that energy at a distance out away, that energy is spread over the sphere. Wave is spread over evenly on the sphere. So the intensity at this point there is just P divided by the surface area. The energy radiated out per unit area. That's right. So our R is the distance, if you like, right? Or radius of the sphere. Right? Wave spread out, the intensity decreases as the inverse square of distance. Right? And then we have also derived this one. I is proportional to amplitude square. I is also proportional to 1 over distance square. Then we can combine the two together. A is proportional to 1 over R. Okay, if we look at the table for intensity, we can see that this one not interest to us. There's the pressure on the eardrum as the sound is received. This is the intensity. The lowest intensity of sound that can be detected for human ear is 1 × 10⁻12, which is this one. Threshold of hearing, we call it threshold of hearing, known as threshold of hearing, and is equivalent to the intensity when someone whispers into your ears. Okay, that's a threshold of hearing, somebody whispering to your ear. A sound intensity of 1 watt meter minus 2, compared to this one, this is very low, this is very high, can cause pain to the ear. Right? So 1 is about car horn. Right? Too loud. Too loud. That can spoil your ear.
No, okay.
So this is a threshold of pain. The car horn is a threshold of pain. Wide variation in magnitude for intensity of sound from -12 to 10⁻3. That is for the jet engine at 10 meter. Okay, so of course it could be higher lah. There could be higher explosion also, maybe not written down there anyway. So pitch and loudness. Sound may be generally be characterized by pitch, loudness, and quality. Pitch of sound is just the frequency. Right? Loudness is subjective. It means it depends on the person, and it depends on the age of the person. Right? An old person having problem listening may say it's too soft. Right? A young person may say it's too loud. So that is subjective, but it's related to amplitude. Greater intensity means greater loudness. Okay. To make a huge range easier to write down or easy to visualize, a second scale of loudness was created called the sound intensity level and is measured in decibel. Right, I hope you have done your homework. I think tomorrow, Saturday, we should finish. Then you should try to complete everything. And you want me to mark and send it to me, right? In PDF form.
Okay.
This unit is extremely useful for when comparing physical quantities that have a huge range in magnitude. Decibel makes working with such large comparison in magnitude easy. Right? It's a log scale. Decibel is a log scale. Right? So remember log scale. This is 0.1. Log 0.1 is -1. Right? Or it's 1/10. 1 divided by 10. Log 1 is 0. Log 10 is 1. Log 1000 is 3. Log 10,000 is 4. So basically, if you like it, the 3 is because of 30 lah. The 4 because of 40. Right? Decibel is a log scale. Either large range or numbers are easier handled on the log scale. You can see that 10,000 is just 4 only. Or that one is of no interest to us, where you go to university, where you using amplifier, you're interested in attenuation, it's easier to use that. So we can convert that, right? The intensity to decibel. One reason why intensity ratios are expressed in decibel is the number involved is cover a wide range. By expressing the power ratio in decibel, calculation involving, I think I'm just repeating, addition, subtraction, multiplication, division. Okay, so instead of multiplying, we can use addition or subtraction because it's about scale. Okay, let's define it. Decibel is comparison of two quantities, I1 and I2, and is defined as 10 times the logarithm of their ratio. Right? Number of decibel, 10 log I1 over I2. 1 bell is 10 decibel. So if I1 is I1, is greater than I2, then you get a positive answer. Right? If I1 is less, I2 is greater, the denominator is greater than numerator, then you get a negative answer. Right? Example 2, double 2 times. I1 is 2 times of I2, then you get 0.301. But if the other way around, I2 is double the intensity of I1, then you get a minus. Okay? Depend on which is greater. Greater one, you get positive answer. Right? If the denominator is greater, you get a negative answer. Okay, sound intensity level is 10 log I over I naught. I is the intensity of sound that we hear. I naught is the threshold of sound that we can hear. 1 and 10 to the power minus 12 watt meter minus 2. Okay, so we have completed this one. Let us go to checkpoint. Try the question before we go further. Two point 2.3, 21.3. Okay, 21.3. I try this one. Find the intensity of sound coming corresponding to the intensity level of 5 decibel. Okay, tell me the answer. Don't look at the answer, work it out. You should have paper and your book with you already. Right? Just using that formula, that's all. I naught is given you. This is your I naught. Calculate your I. This one is given you 5. What's the answer?
3.2 times 10 to the power negative 12.
Huh? Okay, you're right. 3.2 times 10 to the minus 12. Try the other one. What's the answer?
So 1.8 times 10 to the power negative 12.
2.6 is this one. Is 2.6. 10 log. I know it's this one. Okay, calculate it out. Right, 1.8 times. Okay, good. Let's carry on to number 2. Intensity level of 5 meter. 5 meter from the point source is 86 decibel. What's the intensity level at a distance of 10 meter from the source? Right? Calculate the intensity first. Okay, what's the intensity? Yep, what's the intensity?
The intensity is 3.98.
Okay. And 10 to the power 8. Okay, now go and calculate.
Not 10 power negative 4, sir.
How to get negative 4? Right? It's 10 to the power 8. 10 to the power 8, 8.6. You can convert that to 10 to the power 8. Yeah? 8.6. 8.6, then you use 10 to the power x sign to calculate out. Then after that, times your I naught. Okay, can. So far, I've been doing okay. Now, what is the problem? Okay, now go and calculate at 5 meter the intensity. What formula to use? Yep, what formula to use? 2 formulas only. So far, we have given you today. So you should be able to use the other formula that I've given you. Right? It's just that IR square is a constant. R is a distance from the source. Distance of the point of the source. Okay, then calculate your I. What's the answer? Right? No need to calculate I naught because it will disappear later on. That's why they did give you. Yep. What's the intensity? In terms of I naught? Yep, yep. What is the answer? What's the answer? Yep, I2 is a new intensity. R2 is a new distance. I1 is the old intensity. R1 is the new intensity. I2, yeah, R2 down. Got that? Put in your value. That's the I1. R1 is 5. R2 is 10. Then go and calculate out. In terms of I naught. Then go and calculate again. That's it out. That's all. Can?
Can.
Okay, let's go back to our, I say, the reason why you're not doing well is because you're not doing your homework. Okay, checkpoint 21.2. Number 1. Have we done this one?
Checkpoint which one, sir?
21.2.
Did already, sir.
Did already. Okay, then try number 2 then. Sound is produced by a stretch string. Frequency of the second harmonic is 165 Hertz. Calculate the length of the string. How do I do that? I can see that you didn't do your homework. How are you going to progress? You tell me. No wonder your teacher run you down because you don't do your homework. You can never progress if you don't do your homework. You always fail the physics. Yep, how to calculate the length of the string. Any idea? First, you must know what is second harmonic. This is second harmonic. Okay, go and calculate the wavelength. Go and calculate the wavelength. What is the wavelength? Yep. What is the wavelength? How to calculate the wavelength? No idea. Cannot do. That's the problem with you. That's why I say you never do your homework. Never study. How to progress, you tell me. First, calculate your wavelength. Right? Lambda 2 is V over F2. And put in your value. Your V is 330. Right? Frequency is given you. So it's 2 meter. So the wavelength is equal to the length, 2 meter. Right? So the length is just 2 meter. Right? The next one, they ask you to find the frequency of the second overtone. Second overtone is mean third harmonic, no? Right? So you can remember the formula. Right? Second overtone is third harmonic. Remember the formula faster. Rather than go and you can derive it if you want to. You just another loop, that's all. The length is constant. Right? So Fn is NF1. Now you just have to calculate your F1. Right? F1 is from here, is F2. So here by 2. Okay, 82.5. And F second overtone is F3. 3 times F1. Okay.
Okay.
You must make an effort. If not, you are wasting your parents' money. If I have a choice, I also don't want to teach you. Just your mother want me to teach you. Wasting money. Not putting an effort to study. A wire of length 1.20 meter is stretched between 2 points. Small pieces of paper X, Y, Z are placed equally spaced on the wire. It is observed that when the wire vibrates at a certain frequency, X and Z drop off, but Y remains on the wire. Explain the observation. Okay? Why? Why X and Y drop and then Y remain there? Yep. Explain. Why X and Z, right? Is why Y remain on the wire, X and Y drop off from the wire. Why? Yep. No idea. Standing wave is from there. Right? X and Y are your antinode. So the vibration is very large. Right? Vibration at X and Z is antinode. So vibration is very large. So when you vibrate, it will be thrown off. Whereas Y is a node. Right? No vibration. It's a node. It's not vibrating. So it stay there. Draw a diagram to show the standing wave along the wire. That one you should be able to do that. Right? That's how it should look like. That's your X antinode, Y your node, Z antinode. If the speed of transverse wave along the wire is 720 meter per second, calculate the frequency of vibration of the wire. Okay, you should be able to do that. How to calculate the frequency? What is the wavelength? Yeah, what's the wavelength?
Wavelength,
Yeah, what's the wavelength? I already shown you in a diagram already. If you can answer me, I don't know what to do for you already. That's why I say don't put in effort to study. You just use your excuse as phobia. I don't know why you.
wavelength is 1.20.
That's your wavelength. It's already shown you already. Then use the frequency is V over lambda. V is given you. V is given you. Lambda is 1.2. And calculate out. Okay. I think we have done already. Is it number 4? Am I right? Okay, then let's go to number 5. Okay, a small loudspeaker is connected to a variable frequency generator. This loudspeaker is placed at the open end of a resonant tube of length 4 cm. The other end of the tube is closed. If the frequency of generator is increased from 2200 to 2000 Hertz, what are the frequencies and resonance occur? Okay, how to do this one? Right? Go and derive it if you've forgotten. You must know how to derive it. There's a closed tube there. There's a node. There's an antinode there. So you should be able to tell. Cannot remember the formula. L is just a quarter lambda. Lambda 1 if you want to. Okay, how to proceed from here? Yep. You can see every time I teach you, I ask you, you don't know one because you don't bother to study, don't know to do homework. Anyway, I think your mother has to do something about it. If not, you are wasting your money here. That's why I have to scold you. From here, this is a quarter lambda, and take the 4 across there is 4L. L is 40 cm. Convert it to meter. 0.4 is 1.6 meter. Right? Then go and calculate your fundamental frequency, F, V over lambda. Right? V is given you in your value, V, there's a lambda. Okay, so your fundamental frequency, then how am I going to proceed from here? Yep, how to proceed from here? Right? You need to know this formula. Fn equals to nf1. Right? Or if we use F, we can use F here. Or F1, this should be F1, this should be F1. Then calculate. Right? First one is 206. Second one is times 2. This one times, sorry, this one is odd. Right? The first one is 1, n equals to 1. Second one is 3 times 3. This one times 3. Third one is times 5. Right? 1, 3, 5, and then this is times 7. Right? This one times 7. And then 1, 3, 5, 7, 9. So this one times 9 to get this one. After that, you will have exceed the limit already. Okay? Any comment? Yep. Any comment? Anything not clear?
No, clear, sir.
Okay. Let's go to beats. And then we will stop for a 5 minutes break. Okay, so these are all the formulas you need to know how to use. Let's go to beats. Okay, you should be able to do this question in number 13 in your worksheet. Okay, beats 94. Right, beats use the principle of superposition to explain the formation of beat. Use the formula, this one. Okay, so these are your page 94 beats. These are your two waveform. Right? Remember, they must be on top of each other. They must cross at the same point, and that's what you see. Right? Beat is a wave phenomenon produced by superposition of two sound waves of slightly different frequency. These two waves are of different frequency, slightly different frequency. Okay. In this case, one is 50 hertz, one is 40 hertz. The intensity is maximum. So when we add these two together using the principle, then these two can see that this part is 0. That's why we get 0. This part, you add it up, this one plus that one there. That's why you get maximum here. Right? This part, you get back to 0. That's maximum. This is minimum. Get 0 here. Okay, you can add the others. The intensity is maximum and falls to 0 and maximum. Right? Maximum goes to 0 and go to maximum, goes to 0. Right? So you hear, what you hear is called beat frequency. That's a beat frequency. So beat frequency is just the difference between these two. Right? Usually we are interested in positive. So sometimes we may put a modulus there. Right? Where F1 minus F2. Right? In the example, the bit frequency is 50 minus 40. Okay. Any comment? This one is just memorizing, nothing much. Okay. Don't know why they introduced the math part. It just make life more difficult, that's all. Okay. We are just using this equation, this one. Right. Don't know why this is a cost graph. This is a cost graph also. Okay. Different frequency. I don't know why your book give a minus there. Okay, probably they want this one to start at minus. Right? This one to start at minus. Then you add y1 plus y2. Right? Get this formula. You get a minus 2 there. And then amplitude A is amplitude A. Okay, so your x is this is your x. That's your y. Okay, x plus y divided by 2. So these two add together. These two add together, you can take the 2 pi t out. 2 pi t out, f1 plus f2 divided by 2. Right? The 2 cancel off. So they get f1 plus f2. The other one is x minus y divided by 2. So this one minus that. Right? You can take a 2 pi out, 2 pi t out. So you got f1 minus f2 divided by 2. Right? The 2 and the 2 cancel off. That's why you get f1 minus f2. Okay, so that is the equation. And then how do we look at the equation? That we can represent sine pi t into f1 plus f2. And then that one is called the amplitude A1. So the frequency is given by this one, f1 plus f2 divided by 2. Amplitude A1 is just this one times 2A. Maximum amplitude is 2A, right? Where this is 1. Okay, let's concentrate on amplitude. There's a formula. When the amplitude is 0, minimum, right? That part there, 0. Since it's a sine graph, sine 0 occur at tan 0. Sorry, have I done something wrong? Yeah, I think I've done my maths a bit poor already. Okay, let's just continue on. Sorry about that. Right, we want this term to be 0. Right? The amplitude doesn't come in anymore. We want this one to be 0. So when this is 0, it occur at 0, pi, and 2 pi. Okay, so we can calculate our t. Right? Take this one down, 0. And take this one down, you get this one. Pi and pi will cancel off. Pi and pi will cancel, get this one. Okay. So bit. Right? So if we like, we are looking at this part. This part. So neglect this part there. Right? We're looking at this part. So this part, one start with a cosine negative, one start with a sine, cosine positive. Okay. So bit period, we just subtract. This one subtract that, or this one subtract that. That's what we get here. So we subtract, we get 1 over f1 minus f2. So bit frequency is 1 over the period, at the period. So we get f1 minus f2. Okay. Right? If you use both of them cos, right? Since we use maximum, same thing, right? Except that we use this equation, you get a different formula. Right? Just now when we look at here, right? We forget about the other part. Maybe I should cancel all that off. I should block it off. This one we are just looking at the one there, right? Just to help you try to imagine that one there. Okay, for this equation. But now we are looking at the real one, the real equation there. This one, same thing. Right? So we just use a different formula, that's all. This one to help us. Same thing. Right? This is the one that we are looking at. So it shouldn't affect our answer. It should be able to interpret the equation. Okay, so we have completed. Let's try the checkpoint. Right? And try have a look first. 21.4. 21.4, have a look at that.
Okay.
Oi, where's my...
So your screen not showing.
Okay, can you see now? 21.4.
Yeah.
Try this one.
So can you just go on with the class actually? Because 5 o'clock also I got a tuition.
You are supposed to have one class, not two classes together. Yeah, I don't know how to do with you. Sometimes I don't want to teach you. Sometimes give up on you. What a class already, I cannot have another class. Don't want you cancel the class.
Oh, what?
You know that
No. I have another tuition. That's what I mean, sir.
you cannot have two classes at the same time. Right? I always don't finish on time. I always extra 1 hour. Okay. You have not learned at all. I don't know what is happening to you. 1 whole week holiday and then you are not doing anything. A tuning fork is sound simultaneously with a guitar string and beats of frequency 5 Hz. Sorry. There's a beat frequency 5 Hz. And the guitar string is 425 Hz. If the guitar string is tightened a little, the frequency is 4 Hz, becomes 4 Hz. The beat frequency is 4 Hz. Right? What is the frequency of the tuning fork? Okay. How to do that? When you tighten, has the frequency increase or decrease? Yep. When you tighten the guitar string, has the frequency increase or decrease?
Increase lah.
The tension will increase. So the speed will increase. So the frequency will increase. Right? Let the frequency of the tuning fork be F. Yeah. So F minus 425 equals to 5. Okay. Then how to solve the other one? F equals to V over lambda. So when the string is tightened, the speed and thus the frequency of the note increases to X, and let it be X, the new frequency be X. So your F minus 4 minus X equals to 4. Right? Tuning fork is the same. So it's so your F is 430. Yeah, you increase it by 4. So F is have I done something wrong here? Something wrong here. Sorry, done something wrong here. For hers, for hers, for hers, for hers, then your okay, I get 430. How do I get 430? Have I done something wrong here? 425. 425. Oh, what have I done here? I've done here. F minus 425 is 5. Now it should be let me solve for you tomorrow. Let's go to the second one. Two open and resonant tube of length 50 cm and 51 cm produce beats of 7 hertz when each tube is vibrating in a fundamental mode. What is the speed of sound in air? Right? This open tube, 2N open, you are co-fundamental mode. So that is your fundamental mode. Antinode at the open end, node at the center there. Okay, so you should be able to get the length. Right? This is how many wavelength is this one? Yep. How many wavelength is this one?
Wavelength.
Yeah, how many wavelength is this one?
0.50.
Half a wavelength, right? That is the minimum. That's the maximum. So from minimum to maximum is half a wavelength. It's written here for you. Half a wavelength. You should be able to know fundamental mode. L is half a wavelength. Right? So frequency is V over right? Wavelength is just 2L. So that's why you that one there. V over lambda. Lambda is your 2L. That's why we use your 2L there. Right? So F1 is V over right? The total is 50 cm. That's 50. So you get V over 100. And F2, right? F2 is V over 51. 51 times 2 is 102. So F1, right? This is bigger. This is smaller. F1 minus F2. This one minus that one there. Right? Your total is 7.
Hmm?
Okay. So go and calculate this one out. See your calculator. Yeah, this one. And then that difference is 7. And use your calculator. 357 meter per second. Okay. Any comment? Okay. Since we still got a bit of time, we will start with our anything to ask? If not, let us carry on.
Nah.
Okay, let's go to Doppler effect. Let you just watch the video. Can you see the video? Can you see the video?
No, I can't see the video, sir.
I don't see the video. Okay, can see the video now? Talk to me, don't keep quiet. Can you see the video now?
Yes.
In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
the Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
Okay. Let us go back to make a start. Okay, page 98. Describe the Doppler effect.
Hello. In this podcast, I'm hoping to talk about redshift and the Doppler effect,
Sorry.
and how this relates to models of the
Looks I
universe
have to
expanding
switch it
and the
off.
theory that the universe began with the
Can't see the video. Oh.
Okay, can you see now?
Mm-hmm. Then yeah, I can only see the slide lah. Yeah.
Yeah, slide lah. Slide. We are
Ah.
now. We won't start much. We just give a brief so that tomorrow you are ready. Doppler effect, page 98. Right? Describe the Doppler effect for sound and use the derived formula for source and observer moving, right? Source and or observer moving along the same line. So you want either the source moving or the observer moving or both of them moving. Okay, so what determines the color in light? Yeah, what determines the color in light? Yeah, what determines the color in light? You should not, when it comes for tuition, make sure you have a good rest first. Don't have anything to do. Don't go outside and tire yourself out. So your tuition is important. You know you're wasting your money by paying me to teach you and you don't learn anything. Right? You take a rest first before you come for tuition. What determines the color of light is the wavelength or frequency of the color. What determines the pitch of sound? Yep. Pitch determined by frequency. Right? Sound may be generally characterized by pitch, loudness, and quality. The perceived pitch of sound is just the ear's response to frequency. That is, for most practical purposes, the pitch is just frequency. Pitch is just frequency. Okay, so what is Doppler effect? Right, as a fire engine moves towards the stationary observer A, observer B, you can see that the wavefront is moving closer and closer together here, but here is moving far further away from each other. Right, so here you see shorter wavelength. Here you see longer wavelength. So Doppler effect refers to the apparent change in frequency of sound when there is relative motion between source of sound, which is the truck, is the fire engine, and the observer. Right? So both of them can be moving, or the fire engine can be moving, or the observer can be moving. So that's why it means like relative motion between source of wave and the observer. Fire truck not moving, both observer and B hear the same frequency. Right? But when it's moving, then this observer A, when it's moving towards, the frequency is higher. Now, observer B, the frequency is lower. Right? Or longer wavelength. That's how we argue. V is constant. The speed of sound is constant in air. Right? So if the wavelength is longer, frequency is shorter. That's what we hear here. Yeah? Shorter frequency, bigger wavelength. Shorter wavelength, bigger frequency. So when the ambulance approaches the observer, what happened to the sound? Yep. You should be able to tell me what happened to the sound. He just show you the video just now. What happened to the sound? Yeah, two things happen. Yep, can remember?
High pitch generated.
high speed, so high frequency, and then
High, then we'll go to low.
I'm asking you one question only. I didn't ask you any. I just asked you when the ambulance approached the person, what happened to the sound? Two things happen. One is high pitch. High pitch means high frequency. Then what do you hear? As he approach you, what will happen?
Higher frequency generated.
Yeah, but beside higher frequency, there's another thing you hear. Loudness increase.
Oh,
Right? Frequency of pitch increases. Why? Because your intensity, power is given, the power of the sound is given by the police car, if you like, or an ambulance. And if the distance between you is shorter, then it's louder. Right? It's further away, it's softer. Like this one, further away is softer. That should be argue out. When the ambulance receive, right now we are looking at observer B, or move away from you, what happened to the sound? Yeah.
moves away from you. What happened to the sound? Loudness decreases lah.
Loudness increases, then frequency.
Frequency decreases.
Yeah, it's already written for you there already. Show you a picture there. Right? Loudness decreases. Pitch or frequency decreases. Right? So we can summarize that. When the source of wave move relative to the stationary observer, there's a change in observed frequency. Right? So these are the formula we'll use. Speed is frequency times wavelength, and then distance is speed times time, or in terms of formula, x is vt. Right? Then we are looking at moving observer. That's moving source. There's an observer stationary. There's an observer stationary. Right? So if it's stationary, okay. So equation, right? Just summarize for you the equation for observed frequency for moving source. Right? Speed of sound is v. That's the speed of sound. Frequency of sound is constant. The frequency that's sent out by the source is the same. It doesn't change. F. S is for source. O is for observer. Okay, and this equation only apply for the speed of sound greater than the source of sound. Okay, so you need to memorize this formula and know how to use it. Observe frequency, speed of sound, frequency of sound, right? Speed of the source of sound, Fs, Vs, your book use US, right? Negative, when the source is moving towards the observer, right? If you like, this is your observer, if they're moving towards the observer, right? These two are, this is speed of sound, both of them are in the same direction, then you just subtract. But when it's moving away or moving towards each other, then you add them up. Okay. Anything else you want to ask?
No,
So whether plus or minus, you can argue out. When it's moving towards you, you have higher frequency. So it means that this is negative. When it's moving away, when the signal source is moving away from the observer, then the frequency is going to be smaller. So that one must be, you add them up. There's another way. So you look at the speed of the source, the direction, and the speed of sound. If both of them are in the same direction, then you subtract. And both of them are in different direction, then you add them up. Okay.
Okay.
Anything else you want to ask? No point in going any further.
Yeah.
Since our time is up already, we'll carry on tomorrow.
Okay, sure, sir.
Okay.
This subtopic 3.4, right, sir?
Please go and use the real topic name now. 21.4,
Sorry,
not 3.4.
21.4.
21.4.
21.4.
No, 21.5, not 21.4. 21.5.
21.5. Okay.
Right? Review through. Your teacher have already taught you already. You don't want to learn, I cannot force you to learn. 21.5. Okay, I'll stop here.
Okay, thank you, teacher.